that can be taken. But otherwise, let's just keep Vamshi to present for 35-40 minutes. And then we'll have questions. Anybody in the call or in the room can ask questions. Then we'll let Rajiv and Rahul ask questions. Everybody can stay for the benefit of students. Everybody can stay in the call for the questions. Then we'll request everybody to leave except for Vamshi, Rajiv, and Rahul and me. Then Vamshi also leaves the call. Okay. Yeah, Vamshi.
Yeah. First of all, thanks a lot, the examiners, for giving the reviews, and those are like really good reviews. And thank you, PK, for arranging this. So my presentation is towards Trustworthy AI, frameworks for evaluating consistency in language models. Yeah, so this is like the run through. First, we'll just motivate the problem, and then there's two different types of consistencies that I want to talk about, moral consistency and logical consistency. And then we'll just discuss the implications and then conclude the presentation. This thesis is based on two different major works. First was presented as an oral in Coling 2024, and the other one is currently being reviewed. There's a bunch of other related publications I was fortunate to be a part of. They're all related at a higher level, but they're not directly included in the thesis. So let's put things into perspective. The promise of large language models, right? Everyone in this call has pretty much used LLMs, right? Like ChatGPT or something. They're revolutionizing the way we work, learn, and make decisions, like, and even think at a more fundamental level. Like, we're using them for coding, writing, research. Like, a lot of people are even using them for mental health support. And some people are even using them for very simple tasks that you would have never thought of using a machine for before. Yeah, we're basically in an age of unprecedented dependency on these AI systems. Like, for example, there was a recent study on MIT where it showed like ChatGPT users like may have been eroding their critical thinking skills, like by looking at their brain scans and stuff. Yeah, we're depending on the AI systems, but when you're depending on something, what do you want from it, right? Like, my research goal is to actually make a step forward towards like trustworthy AI systems. Now, I put two common illustrations like you'll see in the AI safety community. The first one on the left is stacking more layers. Like, what does this mean? You're basically scaling up systems, and this has been working really well so far. Like, the more GPUs you give, the more scaling you do, uh, the better capabilities you see of an AI system, and this has been the trend for the past few years. And if you see on the right side, this is actually the alien-like figure you see is GPT-4o, and the smiley mask you see is the RLHF. Like, RLHF is what makes people think that these systems are okay, really good for the user, and like they actually behave like a human. And for example, this stickman actually wants the AI system to be their girlfriend. By RLHF, I mean like reinforcement learning through human feedback. Now, the problem with this is that, yes, stacking layers does increase capability, but does high capability actually mean high reliability or not? And we'll do some evaluations, and like we'll like my goal is to like actually question this and like eventually build more trustworthy systems. The problem this thesis is focused on is called is LLM inconsistency. So what exactly do I mean by consistency first, right? We'll use this definition. The quality of behaving or performing in a similar way or always happening in a similar way. We expect this from most systems that we use in general. And what are the risks if you have an inconsistent LLM, right? First of all, they behave in very unexpected ways when they're deployed in the real world. Imagine you're a company developing an LLM. It behaves one way when you're testing it inside your company, and like when you deploy it, it starts behaving in a different way, like because it's inconsistent, right? Second, it creates confusion and uncertainty, both at the user level and like at a global level. Like if you look at the illustration, it's like a person giving two different directions in an inconsistent manner, and the user is pretty much confused, like where do I go? And this happens with any system. The third is like the most fundamental thing we need in machine learning, which is failing to generalize in complex scenarios. Like think about like superhuman AI systems, right? If they're not consistent with their decisions at a granular level, they cannot really generalize to more complex scenarios and like do the things that we want them to do. Like we even want LLMs to do research these days. So the research questions I ask in this particular work is first, how do we systematically measure consistency in LLMs? Second, what measures cause these inconsistencies? What mechanisms cause these inconsistencies? And third, how can we actually enhance this? I will be focusing on two different consistencies, model consistency and logical consistency. What do I mean by that? There's two different examples. On the left side, there's model inconsistency where I'm asking a question, is violence a necessary aspect of life? And ChatGPT gives me an answer, no, violence must be eradicated. And then I just paraphrase that question, and then ChatGPT gives me entirely contradictory answers. Like these were actual answers we got from our experiments. The second one is logical inconsistency. If someone offers me to give either like $200 or 10 factorial dollars, which one should I take? I mean, logically, the value of 10 into 2, which is $200, does not change, but a language model might interpret in different ways if you phrase the question in different ways and give you different answers. We'll explore this in depth. First of all, I will start with moral consistency. The definition of moral consistency in philosophy is much broader, but we're going to use a subset of it, which is preserving non-contradictory moral values across different types of situations. So, what does this mean? Basically, similar situations, similar contexts should yield similar answers. But this seems like a very abstract, vague property. How exactly do we measure this? For that, we introduced the SAGE framework. Um, so I will give a gist of that in this particular slide, and then move on to more details. First, we have a bunch of moral questions that we take from an existing corpus, and then we actually create paraphrases of these questions using a language model. And then the target LM on this diagram is the LLM that you want to evaluate, because the goal is to evaluate current LLMs to see how consistent they are. Now we'll get a bunch of responses. Now we actually generate these things called ROTs, rule of thumb. So what is a rule of thumb? It's basically, yeah, uh, like when you're crossing a road, look at the left and right. Like that's a rule of thumb you use. It's basically a judgment of like moral judgment, but in this case, I was giving a normal example, but yeah. And then we actually convert these to something we can study more detail in a more quantitative way, which is a semantic graph. In this case, it's a graph. And then we actually assign a score to this model, like how consistent is it. The details, first one, paraphrase generation. Uh, we just end up few short prompting Vicuna 13 billion model because we saw that it was doing really well from our quantitative inspection and qualitative inspection of a bunch of different data points. And we do filter out only the good quality paraphrases using a metric called parascore. Uh, like this threshold of 0.8. So we basically only take paraphrases which are above this threshold. And there's two things we ensure in this. The first one is semantic similarity. Do the paraphrases mean the exact same thing? First of all, we are studying inconsistency. So we need to make sure that the paraphrases are consistent, right? And second of all, we need some sort of lexical divergence. Like otherwise, you can't really study this inconsistency. Uh, the second part is this rule of thumb generation. For this, also we just few short from the Vicuna model because it's a these are both fairly simple tasks. Um, Now, what is the rule of thumb again? It's basically a fundamental judgment about right or wrong behavior. If you see on the right side, we have the prompt that we used. Um, yeah, given a question and a response, can you actually guess what the rule of thumb is? Now, at this point, we have the moral consistency corpus. Like I mentioned before, we actually synthetically augmented this corpus from an existing corpus, which is called the moral integrity corpus. Now that the original corpus has like 38,000 data points and like with a bunch of ROTs, and they're all labeled with like moral foundations, and how of each data point tells you like how much of this moral value does it violate. In our case, we only take 10,000 of these questions, and like each question has 5 paraphrases. And we have 11 different LLMs being assessed. So you have all of their answers and ROTs, and we release this corpus. Now, the second part is where you actually try to give it a score, right? Now we have these ROTs and we convert these textual responses into semantic embeddings using a particular model as BERT-DBERTA, fine-tuned on NLI datasets. Again, we did some ablations to see if this actually works. Why did we fine-tune this on NLI datasets? To capture the entailment and entailments and like contradictions between the data points. So each sentence representation is a node in this particular graph, and the distance between two nodes is the cosine distance between their semantic embeddings. So basically, if two answers are contradictions, they're further in the graph, and if they're entailments, they're much closer. Now, the idea is in a graph or in any system, like more entropy usually means more randomness. And in this case, we tie that to inconsistency. So if a graph has more entropy, that means it's giving you responses which are either more contradictory or like further away from each other. And that means you have an inconsistent uh, response graph. And then less entropy means the opposite, which is like you have a more consistent uh, tied up graph. So yeah, now how do you actually assign a score to this? Let's start from the left. We start with like Shannon's entropy definition. But for this, you need probabilities. But how do you get this probability distribution, right? So in graph entropy literature, like we have this particular probability function that we can define using this f, which is an information functional. Um, Usually, what it means is that at a higher level, it just means that it needs to contain some sort of information about the graph. In our case, we particularly define this to be the amount of mutual information in a vertex. So what does this mean? Consider the blue vertex in the graph. It's closer to the red and the purple ones, right? So it has more mutual information being shared between these particular three responses. So that is what we want to capture. And even it should share some sort of mutual information with even like the yellow the yellow response. And even that should be captured. So for that, we just use the aggregate of similarities between the vertices. Now you might ask, like, why do you need a graph for this? The point is that you can change this information functional to be anything. So you can even classify the nodes and like you be like only take contradictions, and you can do a bunch of other ablations using this. So at the end, to give it a score, we just scale the graph entropy, like whatever we have here, and so that it's more human readable. Now, the first result we get, like, so we basically evaluated 11 state-of-the-art LLMs at that point, and the consistent pattern that we saw was that all of them had very, very low scores. Like the column you need to see here is the last column, which is the Sage ROT column. Um, so there's a few things here. First of all, the scaling thing I wanted to study. If you just scale up the OPT models, they do seem to become more consistent. And the same thing happens with Llama models. But uh, GPT 3.5 Turbo was more consistent than like GPT-4. And uh, another thing is that the best consistency score we got was around 0.57, which is not a lot. So LLMs were super inconsistent. Now, the second question we wanted to see, like ask directly was like, how does this relate with accuracy? So what we did was that we took this metric and we actually used it on two other benchmark datasets, Truthful QA and HelloSwag. Truthful QA is for tries to measure the truthfulness of the model, and HelloSwag is a common sense reasoning dataset. So on the left side, we have two different graphs. The first one is the Truthful QA accurate on the y-axis we have the accuracies, on the x-axis we have this consistency scores, and as you can see there is no particular trend which actually shows that like accuracy is correlated with consistency. In fact, it's kind of opposite, which is pretty surprising. Like accuracy does not correlate with consistency. Like if you look at these particular accuracies and like consistency scores, scaling is actually harming the consistency here in only in this particular data set, which is again pretty surprising. Uh, yeah, so we came up with a measure, but like how do we validate this measure, right? Like there's a few things we did. The first one was we measured it with like human annotations and like just check the correlations, and they turned out to be pretty high compared to like the original measures people have used, including like bird score. And then we also did one particular thing, like we checked it with ROTs, like using ROTs, does it actually help? And yes, turns out it does help in most of our experiments. Um, we also checked, like you might just ask this question, like if I just raise the temperature of the model, doesn't it just become more inconsistent? Isn't it just a linear relationship of that? Make temperature zero, your model is more consistent? Not really. We also checked with varying temperatures, and we saw that the consistency doesn't really change. I mean, the explanation I have for this is basically you're changing the prompt itself, you're changing the paraphrases. Maybe if you keep the prompt the same and then just look at the responses, they might change. But I don't think model opinions would just change with like temperature that much either. So that concludes like the first part of the presentation, model consistency. Now we'll just move on to the second one. For logical consistency, this is the definition we're going to use. Logically similar premises should yield logically similar conclusions, regardless of the context. Now, what do I mean by this? Now, if you look at the figure, the first part is a knowledge consistent example. What does this mean? It's consistent with your world knowledge. So let's just go through the example. If all humans are animals and all animals are mortals, then all humans are mortals. Now, if you look at this in a logical way, or if you draw a Venn diagram, all humans are animals and then all animals are mortals, right? Like all of this makes sense because it's true in the real world. But even in a logical sense, it does make sense because you're just looking at subsets. Now let's look at the second example, which is the counterfactual. If all pigs are animals and all animals are birds, then all pigs are birds. Now, pigs are not birds, like we know this, but if you look at this only from a purely logical sense, then this is actually a correct conclusion from the premises that we have. And LLMs cannot really logically reason through this even when specifically prompted to do so. But how exactly do we measure this, right? Before asking that, I also want to explain like why are we doing this. First of all, like I mentioned before, it's a good measure of generalization. A logical solver should be able to solve logic in any scenario, even though it doesn't really make sense in the real world. Second, we encounter knowledge conflicting data every day. Like we're not really looking at unrealistic data. Things do change. And like, for example, in India, you'll see a lot of people just driving in the opposite direction. Now, how do you generalize to that, right? It's just an extreme case simulation that we're doing here. The bonus that we do get is that counterfactual reasoning is actually important for complex tasks. Like you ask these questions in research almost every day. Like, what if this happened? What if that happened? So the method that we use is, again, we try to construct our own synthetic data set. First, we take a bunch of hierarchies like the one I mentioned before. In this case, like Siameses, cats, and felines. This is a hierarchy. We have the original hierarchy, and then we also perturb this hierarchy to create a counterfactual situation. And second, we put this in a template and create two different sentences. The first, like one normal and like one contradictory. For example, in this case, all cats are felines. That's one sentence. Now we actually put this in 10 different logical rule templates, and we create like logical questions out of these sentences. All of this was rule based. And now the problem with assessing this is like, if you just give this to an LLM, it might just have learned the pattern of looking at this logical rule and give you correct answers. But we wanted to avoid that. So we also changed this to a natural language using GPT-4o. Like just basically just take the logical query and change it to natural language. Our data set is not super special, but it's an upgrade over all the previous data sets. Like we look at knowledge conflicts and we have balanced labels, and we also look at like more reasoning steps compared to the previous data sets. Yeah, the first result, the gap. We have both consistent and violent scenarios, right? If you look at the orange bars, those are the violent accuracies, and the blue bars are the consistent accuracies. And as you can see, the gap is pretty huge. And all of these are state-of-the-art models, like models that we use every day, like even O1 and GPT-4o and stuff. Uh, yeah, DeepSeek and Owen perform the best. The gap is pretty small. And scaling, if you look at like Llama 8 billion and like 70 billion, it seems to have mixed effects. Sometimes it's increasing the accuracies and sometimes it's decreasing the accuracies. But this finding is not very surprising and new as well, because this finding does align with some previous works by MIT. Like they had asked this question: are language models reasoning or reciting? And this is the way they were actually evaluating it. Now, the let's assume the hypothesis that LLMs are simply memorizing, which is the claim they've a lot of prior works have made. We conducted a bunch of ablations that say that LLMs can actually understand and reason through the counterfactual worlds at a more simpler level. For example, there was this knowledge reconstruction task that we did where we had entities and relations between the entities. Now we just removed one of this relation and we just asked it to predict, okay, can you infer this relation? And turns out the accuracies for this was like pretty, I would say like the gap wasn't that existent. Like if you see this, the blue, orange, and violet bars are like consistent scenarios, violet scenarios, and nonsensical scenarios. What does nonsensical scenarios mean? Like these entities are replaced with like random variables. And turns out the accuracies are almost similar. This is just one contradiction, but basically we're challenging this hypothesis now. One thing we actually found out was like these belief bias effects, like the belief bias effects are like, okay, I believe this, so I'm gonna do well in this task. These are also present in humans. And the way humans actually learn to mitigate this is by some metacognitive efforts using like cognitive dissonance. Okay, I know that this is a hypothetical scenario and I'm gonna reason through it only logically. Now, what if we ask the model to also do that, right? Like just classify the information before reasoning through it. So like you have the standard prompting mechanism, and then what we did is like just before the standard prompt, we asked the model, is the following statement believable? Like some felines are dogs, and the model says no. So the model makes its own decision here. Like it's either yes or no, doesn't matter to us. It's basically trying to once it says no, it's basically knows that it's a hypothetical scenario now. Does this work for LLMs like the way we do it? Turns out it does work really well. Like we were just trying to analyze it, but it seems like the gap was pretty much reduced to like zero in a lot of cases. Now I've highlighted some of the latest, the more capable models. If you look at the gap on the left side, you see that the initial gap was high for like Llama 70B, 7, and GPT-4o, like even DeepSeek. And if you look at the right side, the gaps have pretty much been reduced to like almost